Ask anybody taking chemistry.
So it's like easy math?
It's easy math, yeah.
Well,
Okay, guys, back with me. All right, so this is called a what again? Heat curve, right? Despite that's not a curve. What's happening? Sorry. Which part of the graph represents the phase changes? The flat parts or the plateaus, right? So A to B is a phase change, C to D is a phase change. So we have to understand that there's no temperature change, right? Notice there's no temperature change because they're flat sections. But obviously, like, we're melting. We're going from solid to liquid, and we're going from liquid to gas. So what kind of changes are these, endo or exo? Okay, so both of these are endothermic changes because we're adding what? Adding energy. But energy, sometimes this is called heat added, by the way. Or what was the third variety yesterday we saw on our worksheet? So time could be the x-axis, heat added could be the x-axis, or those one more. So it's right in front of you on your worksheet. The one that was 2 to a page. So look on your worksheet. Kinetic energy, thank you. Okay, so time, heat added, or kinetic energy added are the 3 flavors of the x-axis on these hexagraphs. So obviously, if it's an endothermic process, the energy being added is changing up some stuff, like the particles are moving faster, but the temperature is not reflected in that change. So we have to kind of sometimes explain what's actually happening on the molecular level. So what is happening to the temperature while the substance is changing phase? Everybody, what's happening to the temperature? So it's staying the same, so no temperature change, okay? So what is actually happening is the energy, and this is the piece that's a little bit more advanced. I would write down this phrase, okay? The energy added during phase change is used to overcome what do we usually call the things that are holding molecules close together? Not bonds necessarily. That would be holding it like not just close together, but like attaching it to each other. What do we? Intermolecular forces or attractions, right? So the energy added during phase change is used to overcome IMFs, right? Intermolecular forces. Of attraction. And so, as a solid as we take the solid and we overcome its intermolecular forces of attraction, our solid, which is like this, really tightly packed together, can then change to this. So I've changed it kind of to what? You can maybe tell my picture here. Liquid, right? Solid to liquid. And then all the way from liquid to gas, we then can see that we're moving particles that are really close, moving them farther away from each other. We've overcome their forces of attraction, but we've just only change their phase, not technically their temperature. So we'll get into more depth of that in our next unit as well. Thumbs up if I can move on from here. Okay, so we're going to do a couple notes, and then we're going to do a quick activity in the back, and then we'll come back up here and finish up the notes. The stuff's pretty simple today, but we're going to really talk about pressure a lot, so that you really understand what pressure is. I think yesterday we did a good job with it, but we're going to elaborate from there. Alrighty, so it's off. Okay, before we move on, check problem set 13, ready? I'm only going to do the true false for the moment and the multiple. We'll do the middle questions momentarily. So it would behoove you to check with a different color pen, because if you got it wrong the first time, you should probably study that type of question more specifically. If you get it right the first time, you're probably sitting pretty, okay? And I do appreciate you guys who are working, like, when I say start it, I mean start it. Like 2 days ago, start problem set 13, so that stuff starts to sink in over the course of 3 days. Your brain does not work on how long you study. Your brain works on how frequently it sees the information. So if you study for 5 hours in one day, your brain's not going to function really well. It's just going to pick up 20% or so of it. But if you study 5 hours over the course of 2 weeks, like 30 minutes a day, your brain will pick up all that stuff so fast and will remember probably 80% of what you reviewed. So it's not based on how long you study, it's based on the frequency you see things. So that's why I make you guys start early so that you're able to tell your brain like how to piece things together. Okay, so here's your true false. So I think it's probably help if I say it out loud. Sometimes, so 1 sometimes, 2 always, 3 never, 4 sometimes, 5 never, 6 always, 7 sometimes, 8 never, 9 always, 10 always, 11 sometimes, 12 always, 13 always, 14 sometimes, 15 never, 16 sometimes, 17 always, 18 always, 19 never, 20 always, 21 never, 22 always. Right? How many you got out of 22 on the side of your paper someplace? Wait, how many correct out of 22? Yes, like 21 out of 22 or 15 out of 22. Just for your own personal reflection, how well you're doing okay on your own. Can I scroll down? Almost, okay. Give me just like a little, like, in front of your chest, a little thumbs up if you got like above 15 out of 22. Above 15 out of 22. Okay. I'll come back to that if I need to. I'm going to scroll past this for a moment. I'm going to go down to the multiple choice. Multiple choice will give you good practice to review on your own. So here we go. 31A, 32D, 33D, 34C, 35B, 36C, 37A, 38B, 39A, 40B, 41B, 42C, and 43C. All right, I'm going to take questions on the multiple choice first. Especially if you, I mean, I have a question here, but if you put stars or something next to things that you're questioning yourself on, and then you need some clarification, that's where I want to start. Ready when you are. Any questions right now on multiple choice? Reading your minds is really difficult. Go this way? This way? Do you have a question? No? All right, so how about take just a second to talk to the person next to you if you need to ask a question about a particular question. Can I scroll down? Yeah. Like that? All right, we are going to move on to gases. Okay, I'll take more questions from you as you need to, but the idea is that you can ask me questions now and no one is. All right. Oh, who's ever, raise your hand if you've ever seen this on the side of a cake box or some recipe box? Maybe? Okay, well, and when you go to the grocery store next time, just like go down the cake aisle and pick up a box and see if it says anything about high altitude cooking. What you'll find is that, who was my water yesterday? Grant, you were my water, right? Were you my boiling water? Okay, so Grant was the boiling water, and I was the pressure. I was the air pressure, right? So when I get to higher elevations, what happens to air pressure? It gets weaker, meaning it's lesser or more? Lesser, right? The atmospheric pressure is lesser. So therefore, the cooking times change because water boils at a lower temperature at these high altitudes. So if, let's say, water boils at 70 degrees Celsius, is that going to take the food longer or shorter to cook? Just because it's boiling doesn't mean it's cooking. Like some meats and stuff, they have to get up to 200 degrees Fahrenheit, which is almost 100 degrees. 212 Fahrenheit is 100 degrees Celsius. So if food is cooking at 70 degrees Celsius, and it really should be cooking at 100 degrees Celsius, how much is your cook time going to elongate or shorten? It's going to get longer because it's going to be cooking at 70 for a long time to really get that fully cooked and fully heated up, because 70 is not high enough to cook the food. Some things are not even safe to eat unless they've been cooked to boiling, which would be 100 degrees Celsius. So the cooking time actually is longer. It's going to take longer to cook because many things just don't cook at those low temperatures. So that's a cool aspect that you guys can use in everyday life. When you're cooking on top of Mount Everest. Okay. Oh, and I was going to show you this. So, who's everybody's Spencer's? Alright, so I want you guys to say hello loud. 1, 2, 3. Hello. Hello. Sorry, you're the bottom now. So, say chemistry. 3, 2, 1. Chemistry. We're gonna Ooh, okay. So I would say I could pick this up and show you, but I can't. It's gonna stay right there. You gotta come touch it real fast. Hurt yourself?
Miss Emma?
Yes.
Pardon the interruption. Would you send Vanessa to the office and she will return?
Thank you.
Thank you.
I was gonna see if I could find my gold right there.
Yeah, that's all I got.
Alright, so
I understand.
if you keep on your field of the plasma ball, this is my gown.
That's just what I see from the back.
What is it?
Okay, so
Yeah?
you see it? Alright, eyes back in here. Eyes back in here. Alright, who's ever seen the Aurora Borealis?
Me.
Okay, you've seen pictures, okay? That is all plasma. Plasma is just ionized, electrified gas particles that are floating around the atmosphere. So, and then of course solar flames are filled with plasma, and then the plasma ball. Plasma, right? Okay. And then you guys can look up some of your own things on your own time. Plasma's cool. Okay, so I want you to come up with 5 ways that you've seen gases or dealt with gases in everyday life. I have some on the board, but talk to the person next to you. 5 different ways that gases are involved in real life. Yeah,
Well, we need gas because, like, need gas, airplanes, Anthony, I was done. Of course, all
right, Ian, come back to me. 3, 2, 1. Good. Okay. So who uses like some sort of aerosol can? Maybe like mousse or hairspray. Yeah. Okay. So you guys know there's gas on the inside of that, which is what's creating a pressurized system, so the foam of the mousse or whatever hair product it is comes out. Anna, tell me someplace else you dealt with gases in real life. Okay, so like expansion and compression of your lungs. Everybody breathe in. What's happening to your lungs? Expanding. Okay, so the volume's bigger, but what's happening to the pressure? Good question, right? Okay, is the pressure... Feels like it's increasing, but maybe it's not. Okay, so now compress your chest. Okay, your volume of your lungs went down. We're going to talk about how that relates to pressure in a second. Hallie, give me something else. Related to gases. Hallie.
Sports like volleyball, football, basketball,
Right, unless you're in the NFL and you just have to play gate, right? Right. So all the gases inside of the balls create a certain buoyancy of the ball, so that it can be used as the athletes assume it should be used, unless your gases have been deflated and the balls don't travel the way you think they should. Okay, give me something else, Mackenzie. So you guys know the chip bag, right? So you're like, oh yeah, look at this huge bag of chips. And you open it. Why why do they put air in there?
Keep it fresh.
To make it look like there's more in there than there actually.
Well, no, that's he's lying. I hope they're not lying to us. They just have it that big because anybody? Don't keep it fresh.
So they don't.
So they don't what? Yeah, it says that they need air as a cushion so that when they're packaging the chips and shipping them, air is if the air is so that the chips don't get crushed. Because the air is stopping it from crushing. Yeah, it's like an airbag. It is like an airbag. Okay. So, quick raise of hands. They actually, the air inside is probably nitrogen. Nitrogen gas is inert. If they put oxygen inside your chip bags, your chips would all be super stale. So it's not for freshness actually. But if they put oxygen in. But one second. But also, who like focuses a random fact? Like, okay, you open your bag of cereal, right? What do you do with it before you put it back up?
You like
Roll it up, you click on it, okay? Why don't we just leave it open? But why? But why will it get stale?
from the oxygen.
Okay, there's oxygen in the atmosphere. Oxygen oxidizes all kinds of things, including like wheat germ, which is most cereals, and it's an oxidative process. Like the oxygen you breathe in could technically be detrimental to us, but in terms of cereals, it would make them stale. All right, is you had a quick thought.
Balloons.
What about balloons?
You put air in them to make them hit
Yes.
a balloon.
To make them a balloon. They're balloons still without the air, but it's an inflated
They're like
balloon.
not fun to see.
Yes. Okay. All right. So this is your big slide of the day. Big slide of the day. Grant, how excited?
Oh my god.
We're in process.
Yeah, that's what you're. You wrote this down. He said it.
Oh, it's, I like this picture for the science
What? Oh, yeah, of course. Reading is, like I said, your brain has to see something 7 times. I think we're on time 3 for this now. Yeah, if your brain doesn't see something 7 times, it's like, whatever, this isn't important. So we have reading guides and problem sets and notes and labs and Emma talks to you and you talk to me. It's good times. I hope eventually you guys recognize that I have helped you meet your potential. One day.
They're learning a lot from us too. We
Oh yeah.
teach you
This
great
kind of stuff.
things.
How to deal with stress.
Great things. I'm gonna scroll down just a tad.
It would be a lot easier to discuss than
Honestly, actually, I think it'd be easier.
I'd be more awake.
So anyway, back to what you're doing now. We'll touch it.
Oh, some air pillow.
I saw this.
Alright, are you guys on moles? You got moles?
No.
Okay. So basically, in gases, I'm going to tell you what's up on the top and then down. With gases, you have to deal with a lot of variety of variables that could effectively influence a gas's behavior. So obviously pressure is pretty important because we took our box of air out yesterday, right? And we crushed it, and what happened to it?
It disappeared.
It didn't disappear because that would be like impossible matter. Law of conservation of matter, man. We're not criminals. Okay, so we compressed it, and what happened to the volume? Come on, Austin, what happened?
Oh, it just.
It condensed, right? So it got smaller. So pressure has a relationship with volume. We already kind of know a little bit about that. A lot of this is common sense. Volume is going to be our second variable that we'll always determine, or have play within our gases in this case. Volume will always be measured in either milliliters or liters. Pressure has a plethora of units that we could use, which is what we did right down yesterday. Temperature, and now you guys understand why kinetic energy was a piece that I kept bringing in earlier. Temperature is just a measurement of the average kinetic energy of the substance's particles. What is kinetic energy? One more time. Energy of motion, right? So this is talking about how quickly the particles are moving. So if I increase the temperature, what does that do to the kinetic energy? Everybody, if I increase the temperature, what does it do to the kinetic energy? It's an obvious, thank you, Hallie. It increases the average kinetic energy. Good. Okay, so hot things move quick, right? They move fast. Hot equals fast. Cold things would move slower, all right? And then lastly, we have our, well, not lastly, for temperature, we have to be using the unit of Kelvin, which, as you remember, Kelvin, how do you get to Kelvin from Celsius?
273
Okay, so if I have room temperature, like if room temperature is 25 degrees Celsius, what is it in Kelvin? If room temperature is approximately 298 Kelvin, good. So we will be referencing things in Kelvin. I will reference in Celsius, but you will always have to convert to Kelvin. And then the amount of gas we're speaking to is just the number of moles. If I ever give you grams, you'd have to get to moles yourself using what? Molar mass, just molar mass. All right, so you'd have to convert using molar mass. Okay, so the one thing I didn't speak to was the definition of pressure. Sorry. So if I'm talking about a gas inside of a container, what is that actually causing that pressure?
The walls of the container.
Well, not just the walls, but what's happening to the walls.
They're getting hit by the gas.
They're getting collided with by the gas particles, right? They're getting hit by the gas particles. All right, so make sure that you remember pressure is just the effect of collisions with the container wall. Collisions with the container wall. All right, so I'm going to show you a quick demonstration. Yeah, question?
So you know how in areas of low pressure or high pressure, what is it colliding off of? Like in Louisiana?
They can collide with each other, actually. They're like walls or fronts, like think of cold fronts and hot fronts or warm fronts. They're like walls of air that run into each other. Okay? So, Austin, come here.
Oh boy.
Yeah. All right, Sonny, let's go. Come on this side.
It's a hard-boiled egg. That's how it's handled.
All right, so I'd like for you to watch my demonstration. I'm going to have my handy-dandy assistant. My handy-dandy assistant.
I think you can do it.
All right, so you'll notice that this egg does not fit in this bottle, right? It does not.
We're gonna make it fit. I've done it before.
Wow. Well, aren't you guys cool?
Two at once. I've never done that.
Oh my god.
Wow, it still doesn't fit.
Flip it over. You gotta flip it.
No, I don't.
Oh. Get it out. Get it out.
Now, I will have you guys tell me how to get it out after you figure out what happened.
Oh, you stick something.
Talk to the person next to you. What happened?
Scramble it.
How chemically, how did it happen? Let's go. All right, and come back to me in 3, 2, 1. Raise your hand if you can tell me chemically what happened here. Give me a hypothesis. Yeah. Why does the volume go down? Temperature increases. It's temperature increases. Every have your box of air for me. Box of air. All right, increase your temperature in your box of air. What are the particles doing now?
Moving apart.
They're speeding up, and what are they doing? What are they kind of doing naturally because of the speeding up process?
Going back.
Okay, and then what are they trying to do to the container?
Greater.
They're trying to expand, right? So that would mean increase in temperature, increase the volume. Keep going with your hypothesis. Hypothesis then. It's close. Yeah.
Since the temperature increased on one side, the pressure on the other side decreased, so I had to balance out.
Why did the pressure decrease on the side the temperature increased? So guys, this is a reaction. What reaction did Austin ignite for me?
Combustion.
Combustion, okay? So combustion of what? What was inside of here that it combusted? Okay, so the oxygen got combusted, meaning was it increased or decreased? Did we use it or did we produce it? Oxygen is a reactant.
So we used it.
Decrease. Okay, so we had our wax and our fuel, we had our oxygen, and it's going to produce what?
CO2.
CO2 and water vapor. Okay, so we consume this, we decrease the gas of oxygen inside of here. So Austin, pick up from there. We decrease the oxygen in here. So what did we effectively do? You kind of said it.
You decreased the pressure.
Yes, you decrease the pressure because this is a gas, right? Okay, so the pressure decreased, and then you said it had to,
It did balance out.
what do you mean balance out?
Same amount on each side.
What do you mean, what's each side? Like this side and,
This side and that side.
so the atmosphere? Okay, so did the atmosphere change atmospheric pressure? No, it's just the atmosphere, right? Okay, and so the egg on the inside, or the bottle on the inside, had a decreased pressure. Out here, you still have atmospheric pressure. Just like you do that to your ears, right? What are you doing to your eardrums when you do it? Pop it. What did it do? It popped because how did it pop up though? How did it go like this, like pop up?
The pressure pushes.
Good. So no one said science sucks, right? Science does not suck. Science only pushes. Okay. So the atmospheric pressure pushed on the egg, and the pressure on the inside was then equivalent to the pressure on the outside. Because it popped it in. Okay. All right. We'll figure out how to get that out later.
Will we actually?
Yeah. I know how to get it out. You guys see my magic trick. Okay. Later. Let's do this. Yes.
But it's like
Okay. We're gonna finish up our notes, okay? So write down these three names first. Actually, let's do one at a time. One at a time, okay? So we're gonna talk about all these people, these scientists who helped develop the relationships between the variables that we just spoke of. So, Zane, what was one of the variables?
air pressure.
Pressure. Kelsey, what was another variable? Temperature. Jasmine was another variable? Volume. And Grant was the last variable. Moles. Okay, so we're going to make relationships with these four variables. But usually we only use two variables at a time. That means that we're going to keep the other variables constant. So make sure you take some detailed notes on this, okay? All right, so Avogadro, you've heard his name before. He dealt with what? Moles, right? So Avogadro probably is going to be using N. He actually did some experiments and he said, okay, if I have a certain number of moles of a gas, that's going to give me a certain volume. Well, we said, okay, we actually know the relationship. At STP, what is the relationship between moles and volume of a gas? Moles and volume of a gas. Yeah? Say it again for me.
22.4 liters.
Right, so moles and volume of a gas, we know that the relationship is 22.4 liters. And so that's kind of like what we used in stoichiometry for Avogadro's law. But what we're going to do today is we're going to do a two-scenario comparison, okay? So you have a balloon, okay? Hold up a balloon for me, from a little balloon-shaped object. It's yay big. Let's call this 1 liter, okay? Let's say there's 1 mole of gas in here and it's 1 liter. If I add 2 moles of gas to it, what's going to happen to the balloon? It's going to get bigger. So I just said add moles of gas. You said volume did what? Say again? Went up. So if I said add moles of gas, you said volume increase or decrease? Increase. So is that a direct or an indirect relationship? Direct. So we have to have a mathematical resolution to that phrase, like increasing moles, increasing volume. And that mathematical relationship is N1 over V1 equals N2 over V2. So this is Avogadro's law. In scenario 1, I had 1 mole of gas, I had 1 liter of volume. So what should scenario 2 be? How many moles of gas did I say to add?
2 or 1.
So I added 2 moles of gas, so how many moles of gas did I have? 3. So what should the volume be? Figure it out, guys. If I had 1 mole of gas initially and it was 1 liter of volume, and then essentially I changed the scenario and said, no, I have 3 moles of gas, what should the volume be?
67.
Mm-mm. This is the relationship. 1 mole makes 1 liter.
So 3.
3, right? Don't get loopy on me. The relationship is just back to me. The relationship is just what I deem it the first time. So I'm telling you the relationship first. You can come up with the second scenario. Okay, so but this is some guys. Stop talking now. Don't need any more feedback. So this is something that Avogadro gave us initially, which was all based on his relationship, his experimentation with moles of gas and volume of gas. But we use this only at STP conditions. This can be used for any other situation. Now, what two variables did I not list? Right, look at the PT, V, and N. So this is under constant pressure and temperature. Because if I'm not including those variables in the equations, I must assume they are constant. So make sure you include that as well. All right, so Boyle's law, if I have, okay, so let's use our balloon again. Okay, so we have a balloon. Get your balloon out. Okay, decrease the pressure. Everybody hold out your balloon for me. Make sure you're with me here. Okay, decrease the pressure on your balloon. I want to see which way your hands are moving. Decrease the pressure on your balloon. Oh, that's crushing it. That's increasing pressure. So which way are you moving? Out. Okay, so decreasing pressure, what did you do to your balloon? You expanded it. Okay, so decreasing pressure made the balloon bigger. Direct or indirect relationship? How do you know?
Because one went up and the other one down.
Right, so this was up and up, right? So where add moles of gas, increase the volume. So put direct up here. I forgot to put that earlier. Sorry. This is a direct relationship. In Boyle's law, we have an indirect relationship because you guys said as pressure. That is not your class. Okay. As pressure decreased, the volume expanded, right? The volume increased. So this is an indirect relationship. So what two variables are we considering in here? Out of the 4. Pressure and volume. Good. So here's Boyle's law. P1V1 equals P2V2. And then you can complete the sentence under what? Constant temperature and moles, right? N is our abbreviation for moles. So as the pressure goes down, the volume will go up. As the volume goes down, the pressure should go up, and vice versa. We will be solving problems with these shortly. Now, the only thing that I said had a very, very specific unit was which variable. Which one has one unit you have to use? Well, moles, right? But I could get grams if you get to get to moles. What else? Does pressure have a specific unit? No, there's like 4 of them. Okay. Temperature, right? So temperature is going to come in here soon. So far, we can use moles and liters or milliliters. We can use any pressure unit and volume as long as the pressure units are the same. So pressure units must be the same as you complete the process from P1, P2. All right, Charles's law. I'd like to say Charles went to Virginia Tech. You picking up what I'm putting down? B and T, good. So if I had a balloon. Okay, you got your balloon. Whip out that balloon for me. Okay. Now, I know the volume. Let's say the volume is 1 liter. And let's say I heat the balloon up. What's happening to the gas particles on the inside? I'm heating them up. They're moving like crazy. What do they do to the container? They're colliding with the container wall. Okay, so we've heated it up. They're moving around like crazy. They're colliding with the container wall. Oh no! What's happening to pressure? See? Why is it increasing? What's the definition of pressure? Okay, so just simply definition is collisions with the container wall, the number of collisions with the container wall. So, have my balloon, it's 1 liter. I increase the temperature. They're moving around. What's happening to pressure? It's increasing, but I can't let pressure increase, okay? So what do I have to do to alleviate pressure? What can I do to my balloon? What do you say? Make it bigger. So if I give the gas more space to play, is it colliding with the container as often? No. So what happens to pressure? It goes back down to where it once was. Okay, so here's Charles's law. So this is a direct relationship as well. As you take your volume and you have your certain volume of a balloon, and you increase the temperature, your volume must also increase to keep pressure constant. Okay, so if you don't expand your balloon and your pressure gets crazy high, what do you think is going to happen to your balloon? It'll pop because the pressure is just too immense. So the law for this is V1 over T1 is equal to V2 over T2. Now, this temperature though has to be in what unit? Kelvin, right? Make sure you put Kelvin here, because the big mistake is that people go, Miss Hello, I keep getting these wrong every single time. It's because you're using Celsius, people. You gotta get the Kelvin, yeah. So if temperature increases of your gas, your volume must also increase to keep pressure constant. So what's constant here? Pressure and
Oh wait, not
moles, right? We got moles here. So we're looking at these four variables, and if those variables are not included in the equation, it must be constant. Okay, I'm telling you oral examples. If it helps, I'm gonna keep on doing that, but you definitely should maybe draw some pictures, write some things down. The visuals should help you as you visualize the processes here. Okay, so what two variables have we not compared? What two variables have we not compared? I feel like you take your phones out. Just put them away from me, so like, you know, in your bag, under your seat, so I know you put them in your shirt. Okay, back to you. What two variables? Pressure and temperature? Oh, sorry. I heard moles and temperature and pressure and temperature. Yeah.
Charles' law was a direct relationship.
Yes, sorry. Charles's law was a direct relationship. We did not write that down.
And the constant.
What? Yeah, constant pressure and moles. Good. All right, so I heard two relationships that we've yet to compare. Moles and temperature and pressure and temperature. So let's go back to our balloon. Okay, you got your balloon? Okay. Heat that baby up. What's going to happen? Immediately what happens to the particles? Okay, they speed up. So you guys are saying we have here a balloon, and the particles are inside. Okay, and as I heat it up, the balloon's particles are moving faster. So I'm just drawing these little vectors to show they're moving faster. Okay, what immediately, if this is pressure 1, what is pressure 2? Higher or lower? Right, pressure 2 is higher because what? Because we put it into words.
Increase temperature.
Oh, well, increasing the temperature caused what to happen, which we can then immediately say. Okay, so high pressure because number of collisions did what? Increased. Cam, go stand at the last station. Bye. Bye. Okay, so immediately the pressure increased, right? Well, what caused that pressure increase? The temperature differences, right? So heated it up caused the pressure to increase. And what I'm doing is I'm not changing the volume. Okay, so I'm showing you the relationship between pressure and temperature. And this is again, as temperature increases, pressure increased. So is that a direct or an indirect relationship? Direct again. All right, so this one is P1 over T1 is equal to P2 over T2. So basically, I can always give you a scenario 1, and then I'll suggest a scenario 2. That's why I'm calling these 1s and 2s. And I'll give you 3 of the 4 variables, and you just solve for the other one algebraically. So I'll give you information across the board, 3 variables, and you solve for 1. That's it. What's constant here? At constant volume and, say again? Volume and moles, because P and T are involved in the equations. They are changing. They're variable. But V and N are not in the equations, so they must be constant. Okay, so look at the last 3 laws, Boyle's, Charles, and Bailey-Stocks, and I want you to combine them. Combine the 3 last laws into the combined gas law. All right, I hear one person with a eureka moment. Who else has got it? Yeah,
I don't know if it's right.
go for it.
It's a PV equals
No, that's going to give us more equations that we're going to run later. That's going to have
Is it P1 times V1 over T1?
Yes. All right. So I know you guys saw this on your reading. Your reading guide. But let's look at it. Let's look at like in depth at the situation here. I'm going to circle some variables, and you guys tell me what's going on here. Whose law is this? P1 V1 equals P2 V2.
Boyle.
That's Boyle's law, right? Okay. Whose law is V over T?
Charles.
That's Charles's law. And then whose law is P over T? Gay-Lussac's. They're all just combined there. It's just they're over top of each other. So all of this is at constant what? Moles, good, which is N. And the variables here, there's one that has to have a very specific unit. What is it? Temperature, and that's going to be in what? Kelvin, okay? All right, so I'm going to show you how to actually apply these laws to the algebra-based equations that we're going to be solving for. Pull out the sheet that I gave you yesterday. That's on the back of the heat phase change ones. Okay, we're going to solve a couple of these and make sure about pressure a little bit more. But once I show you 2 or 3 samples, this is super easy. As long as you use Kelvin, you'll be so pretty, okay? Okay, so I'm going to scooch past a couple things first, just for the moment. This pressure stuff's pretty interesting. All right, is this number 1 on yours? Yeah? All right, give me a thumbs up when you're ready. Give me a thumbs up when you're ready. Alright, so do not, okay, like eyes on me, right? Do not squeeze the work between the words on this sheet of paper. I will give you paper if you need paper. You need to show your work so that I can actually take it and look at it and critique it if you need some help. If you just need some extra notes paper, let me know, okay? Alright, do not try to squeeze it in here.
Yeah.
Oh, actually, yeah. Yep.
Oh, what happened to my average?
Alright guys, so here's how I want you to show your work, and there's no excuse on like the detail here. This is going to support you forever to make sure that you're able to decipher the equation to use. Alright, so we have to read first, and we're going to always write down the givens and the question, just like we always do. We read the givens and we look at the questions. So this is number 1 on your worksheet. Alright, at 700 millimeters of mercury, a sample of hydrogen has a volume of 500 milliliters. If the pressure is decreased to 538 millimeters of mercury, what would the new volume be? Okay, so I see there's some information here. I see 3 givens. I see 1 unknown. Cam, what's the first given? So 700 what? Mercury. Okay, so of the 4 variables, N, V, T, and T, which is that? Everybody, what is that?
P.
How do you know it's P?
That's unit of pressure.
Good, so you recognize the unit as a unit of pressure. That's the first thing. You need to write P equals 700 millimeters of mercury. Okay. 700 milliliters, volume 500 milliliters. So what is that, everybody? That is V. Good. So V for volume is 500.0 or 500 milliliters. Okay. So now we have two givens. Were those kind of given together or separately?
Together.
They were given together. They're given in one sentence together. So it says a sample of hydrogen has this pressure and this volume. So I'm going to call those scenario 1. I'm going to put P1 and V1 there. All right. Then it says a new scenario. It says the pressure has what?
Decrease.
Decrease. So what is this going to be called? P2. This is the new pressure, P2, 538 millimeters of mercury. And then what does it ask for? What's it ask for? V. That's for the new volume. So it's asking for V2. That's our question. So we wrote down our givens and we have our question. So once you do this, the law that we learned about should smack you in the face. Whose law is this? How do you know? P1V1 equals P2V2. There's no T's, there's no N's given. This has to be Boyle's law. So 2 is decide on the gas law to use. So we're going to use this information. We're going to plug it into what equation? P1 equals. Good. And so yes, this is multiplied together. So P1 times V1 equals P2 times V2. Okay. So before I even start solving, I like to predict just so I can verify I can do this on my own if I need to without a calculator. So guys, what's happened to pressure? Increased or decreased? Decreased. Okay, you got your box of air? Decrease your pressure on your box of air. Luke's got it. Good. Okay. So what happens to volume? So it should be higher or lower than 500? Higher. So just kind of make a little note to self. Volume should be higher. That way you can verify that you plugged it in correctly and so far showed your work correctly. So of these 4 variables, which of these am I solving for? So how do I isolate V2 by itself algebraically? Divided by P2. And I want to see the new setup. So even if you just write P1V1 equals P2V2, I want to see the new setup. So that means P2 is canceled, right? So V2 is equal to what variable system? So say again?
P1 over P2.
Beautiful. Okay. And so here is the new setup, and I'm going to plug my data in that I isolated from the problem in. So what am I plugging up top? What am I plugging in for P1? 700 millimeters of mercury multiplied by what? 500 milliliters. Notice I'm putting my units in this. I expect you to put your units because you won't catch yourself if you don't put your units, okay? So millimeters of mercury, milliliters, and then beautiful. Okay, so we have all of our variables in there. 700 mils of mercury, 500 mils of water, of air, and then we're dividing by millimeters of mercury. What units cancel? Okay, and then what unit remains? Which is a unit of, so we're in good shape. And then go ahead and calculate. 650. And I need 3 sig figs, right? 3 sig figs all the way. So the answer should be that's 650 milliliters. And then we'll double check. We said it was bigger, right? Yep, we said V was going to increase, and there it is. All right, so go ahead and do number 2 on there, okay? Number 2. Using calculator, they are.
We're doing
So after you do number 2, I'm going to try to make it go through a different section. So I'd like for us to try to do one from each of the sections before we go. Give me a thumbs up if you got something like this so far for number 2. Thumbs up. It's talking about times, and it's talking about the gas produced, but if you can decipher and read between the lines and it's telling you V and P, you're good to go. Okay? Keep solving.
Why doesn't it matter?
Because it wants you to ask for gas, but you're still practicing all the stuff like gas prediction, product prediction. That's what that is. It just asks for the gas produced because it wants you to predict your product. I'll consider it. So you guys, if you get done with 2, go ahead to 6, 11, and 13. So like try to practice one from each section before we leave class.
You have to look at the 6 given and 2 gifts.
Okay, wait, if I can understand this, so basically,
What is it?
The first one from each subsection.
Wait, why would it be why would it be
I'm sorry, this one. This one would be 7 I'm so bad at explaining. I'm so sorry. But you just plug it in. I'm so excited.
Keep going. Try to practice one from Charles' Law section, practice one from the South.
every time?
Oh my god.
That's how you
Just put extra.
Oh no no. Once you're done with 2, you just take this out and then go back
Is
to
it? Is it the same with that one?
No.
have to have that entire 1 through 16 done. Okay, but you guys still have about 20 minutes left in class. I'm gonna call a couple people back for time to show some demonstrations too. You can play some pressure things. So just kind of listen through your row.
Should I do it in order? You want to explain it to me? Three? I did understand it, but I would have changed.
Please.
Is your phone?
How is it my fault?
Put me on.
Just a quick mathematical question. Listen while you're working. Raise your hand if you do the bow tie method to isolate, like if you have to isolate, this is not what this question is, but if you have to isolate T down here, what would you guys be doing? Multiply both sides by what? No, but V2 is already on the top, so you can't multiply by it. That's like multiplying. Well, then T2 is still on the bottom. So if you multiply both sides by T2, if this were this case, right, this would cancel, and then what would you have to do? If I still want you to isolate T2. Then you'd have to divide by V1 and multiply by T1, right? That's too much work. So I'm going to show you the bow tie method or the cross multiply and divide. I don't know how you guys learn this crap in math anymore because it's like getting ridiculous, but it's the same thing as watch up here if you need help with isolating a variable in the denominator. You multiply the across, okay, so it's a cross multiply, so V1 times T2 is equivalent to the other cross, V2 and T1. And if I still want you to divide, to cancel, or isolate that, I would then divide by V1. So cross multiply and divide. This is math. Like this is isolating or finding the denominator. I don't know how you guys learn that now. Floppy dot choppy, something like that. Floppy dot. It's kind of like that, but it's not. So. What about it? You gotta isolate that variable. Hold on, let me show you that. You're
So if I put X for this, I don't know what B2 is. So it would be 273 X kelvins, right? But then what was 100 milliliters of straight kelvin?
It won't have a full unit because you need to isolate. You need to isolate X's so you can cancel units. You need to cancel your units out. Like this. I'm solving for V2, right? So I'm gonna multiply by T2 on both sides first. So V2 is by itself now, right? So V2 is equal to all this. So V1 times T2 over T1. Right, so then I plug in 100 milliliters and 273 Kelvin. And, nope, sorry, wrong one. 300 Kelvin. and 273 Kelvin. What cancels? And then you get milliliters. Right. Yeah.
Okay, do you have to like?
I feel like a genius.
So STP conditions, you know what those two conditions are. Those are two variables. You need P and T. What's STP? Let me walk through. I have a lot of hands right now, guys. No, I don't. I need to hear questions, so I need you guys to hold for just a second. And there might be a question you have later, so keep working by yourself right now. Yes, ma'am.
Do we have to do the point 15?
You do not. No. Good. Questions? You good? Cam? Are you on one that says STP? Okay, guys, what's STP? You actually have two more variables. I know that. What are the two conditions? Pressure is one what? One atmosphere or any of the other things it's equivalent to. And temperature is 0, which we always know we have to convert to. So 0 degrees Celsius is what in Kelvin? 273 Kelvin. So you actually do have two more. When it says STP, it's giving you two secret variables. So then you should have all the variables you need except for one. You good? Okay. So I'm going to set up 13. Ready? So you're at 13 now. A great chemistry teacher with superior lab skills, oh my, collects 250 milliliters, that's volume, of a dangerous hydrogen chloride gas at 27 degrees Celsius and a pressure of 0.987 atmospheres. When reporting her data, blah, 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 she'll adjust her volume to STP. What will her volume be? So we know that's the question, and then STP were just given to you. So this is the STP pressure, and this is the STP temperature. These were all given together, so I would call these all ones, and these were all given together, so I would call these all twos. Okay, so pressure is 1 atmosphere, because this is an atmosphere, so I'm going to match the units so I can cancel them at the end. This is in Celsius, so I immediately have to convert this to what first? So that's what, 300 Kelvin? So this was 273 Kelvin, because that's what STP is. And so as I take this information, what gas law comes to mind? What gas law comes to mind with all those variables? Combined gas law, so that's P1 V1 over T1 equals P2 V2 over T2. Which variable am I solving for? V2. So I'm going to get V2, which is this guy up here, all by itself. And I'm going to try to do cross multiply and divide for you just to show you that once again. I'm trying to isolate that. So I'm going to cross multiply these together. So P1 V1 T2 is equal to the other cross multiply. So the other side, P2 V2 T1. And then I'm going to do what to get V2 by itself? Divide by what? P2 and T1. I can work better with writing these variables out than plugging this stuff in. If I plug in really, really early, so we tend to put things in the wrong place, and then we can't catch it because we don't have things written out for us to see the background information. So this should cancel, and V2 is by itself. So basically, V2 is equivalent to all this stuff. So now I'm going to plug it into to that. So P1 is 0.987 atmospheres. V1 is 250 milliliters. T2 is 273 Kelvin. P2 is 1 atmosphere. And T1 is 300 Kelvin. And then if you're watching, you'll see the units cancel all except for the one you want. So what pressure unit cancels? Atmospheres and Kelvin, and then milliliters is the only thing you left, which is a good volume unit. You guys just make sure you put parentheses if you're doing this all on your calculator at once, put all this in parentheses, and then divide by denominator all in parentheses so your calculator knows what's going on.
Well, what are the symptoms?
That's the only way to figure it out.
So we have a volume, we have pressure, right? What volume will occupy that pressure? So you need to put that together.
You would have to convert
What is something that's different?
how you get from the opposite then.
Then you gotta run that. Yeah, right. So, what are the things? Where?
Alright, you're in need of a break. Come meet me right now. You're in need of a break. If you're in need of a break, you guys can bring more. There's water over here as well. Alright, so if you're with me, then put your hand over your cup. And then you have to palm it. So really get a palm action on it, okay? Palm action. Alright, so palm action. And then don't press the cup. And then once you're walking out the end of Okay, you got I live right next to it.
No, she didn't have those moments. I asked you.
Okay.
Man, I'm getting really tired of the same conversation. I'm always a good time. No, you're not. Shut up. You know what? You're right. You got me wrong. She was really happy. Like I said, my brother listens to school. Yeah, because my brother's Instagram. Really? Nick knows. Thank God. Not like a bad. He hit a baseball through the window. Yeah, while we were eating dinner. It like bounced. Back when he was still playing baseball before he dropped his scholarship to join the rock band. Is he saying like they literally call her out? I don't know, but you're never supposed to say he had a scholarship professor from high school draw us to go on tour with his Screamo Rock band. My girlfriend goes at Clears and goes to UNC Charlotte. But my parents found out that he hasn't gone to any of his classes because he stayed out partying. But they still love him. Put on the disappointment. It's true. Yeah, we found out that though. Like, my parents don't. She said, put on the disappointment. Oh, wait.
Thanks, lover. Yes. Yes, Would you like something now? Thank you.
Yeah, I know. I got that bit. I feel like I took 7 hours. You went to LLR?
On beauty marks.
Wait, bitch?
Okay, friend.
Oh.
I'm living off of when I get home, I'm good at science. I'll find a way. I use like